Hello everyone. Uh, Welcome to the ninth weekly live session of the NPTEL course of Remote Sensing Principles and Applications under NPTEL and the SWAM initiative. I am Abhishek Chakraborty, a PhD student under the Prime Minister's Research Fellowship Scheme from the Interdisciplinary Center for Water Research IISc Bangalore at IISc Bangalore, and this course has been tutored by Professor Ishwar Rajshekharan from the Department of Civil Engineering at IIT Bombay. So first things first, just the general information which I give always before starting every weekly live session. First of all, the video recordings of the session will be made available on the YouTube channel. I've already uploaded uh, all of them till the last weekly live session. The files relevant to the sessions will be made available through a Google Drive folder. Again, all the documents have already been submitted there, so you can feel free to download it from there. The files and the video recordings will be made immediately available at the class, so I will try my best to upload them within 30 minutes to an hour after the class ends, after the weekly live session ends. And finally, the images, if I've taken them from internet, they are solely for education purpose. We don't uh, intend to plagiarize anything. It's just for education. So far we have finished 8 weekly live sessions, and I've also uploaded the video recordings of the weekly live sessions in the YouTube channel, which I've already shared with you. This is the link for the Google Drive folder, uh, which basically will have the links for the YouTube videos as well as the documents which will be uploaded regarding the class. So today we are moving into something new into this course regarding orbital velocity, orbital speeds, and the kind of satellites. I mean, whether they are geostationary or polar or near polar. So we are going to do something quite unique from today's weekly live session. So let's solve a few questions about them and get to know them better. So first of all. Let me check whether I mean, recording it or not. Yeah, I am. The first question is that the geostationary satellites are located at an altitude of. Okay, so geostationary satellites are located at an altitude of nearly 36,000 kilometers from the surface of the Earth. So the altitude would be in D. So this would be the correct answer anyways, but I will just give a few more information about it so that we can build up towards the later questions in this part itself. Uh, so geostationary satellite is at geostationary orbit. Geostationary orbit or geosynchronous orbit, okay, is near circular geosynchronous orbit 35,786 kilometer, which is nearly 36,000 kilometer. Okay, nearly 36,000 kilometer in altitude above the Earth's equator, and it follows the direction of the Earth's rotation. Of the Earth's rotation. Okay, so we are done with it. Let's try to understand how their altitudes are actually determined. But before that, let's talk about the typical properties also. Typical properties of geostationary satellites. Okay, so first of all, inclination is 0 degree. Then period is in general 1436 minutes, which is also known as one sidereal day. And eccentricity is 0, means it is completely circular. So eccentricity basically measures how elliptic the body's path is. When the eccentricity is exactly equal to 0, that would mean that the path is completely circular. So this means it is circular, which is what happens in geostationary satellites. Now let's try to understand the mechanism behind the altitudes. Derivation of geostationary altitude, let's check it out. So for circular orbits, around a body, let us say that of the Earth, the centripetal force is maintained by the gravity force. So this is basically the centripetal force to maintain the orbit. And this is the gravitational force acting on the satellite. Just give me 1 minute, please. So we need to equate these two equations, and then we need to further use the Newton's universal law of gravitation to come into an expression for the altitude of such geostationary satellites. So let's check it out now. From Newton's universal law of gravitation. So Newton's universal law of gravitation states that the gravity force between any two bodies and the attractive gravity force between any two bodies is basically directly proportional to the product of their masses and inversely proportional to the square of the distances. It's very easy to understand. So this Fg would be G. G is the constant of this term. Me ms by r square, where Fg is the gravitational force acting between two bodies. Gravitational force acting between two objects. So these two objects may be the Earth and the satellite. Me would be the mass of the Earth, which is nearly equal to 5.9736 into 10 to the power 24 kg. Okay. Ms may be the mass of satellite. It would vary with respect to the satellite, of course. And r is the distance between these bodies' center of masses. Okay. And capital G, we all know, is the universal gravitational constant. Gravitational constant, and it is basically 6.674 into 10 power minus 11 meter cube per kg per second square. Okay, so we know that now. Now let's move into the other part. What about the centripetal force? How to find it out? So acceleration A of a body given it is in a circle. We know that from our concepts from uniform circular motion, A would be equal to V square by R, or smaller. Let's keep the notation same. Okay. So where V is the velocity magnitude. Just a second. V is the velocity magnitude. Okay, let me hide it first. That is the speed of the satellite. Fc, the centripetal force, would be ms times v square by r. And now let's go back to the original one, as Fc would be equal to Fg for a motion of a satellite around the Earth. Ms times v square by r would be g me ms by r square, just equating the two terms. So we get v square equal to g me by r. Now let's replace the v with something else. Let's see that. Replace v with equation for speed of an object moving across a circle, of an object moving across a circle. Let's do that. Okay, so we will get the total distance by total time will give you the speed. Okay, because speed equal to distance by time. So total distance is the circumferential distance which the satellite travels around the Earth. So that would be 2 pi r, because it is circular, divided by the total time. Let it be capital T square is equal to, because it was v square in the previous case, v square equal to g me by r. Just equate it. Okay, where capital T is something known as the orbital velocity. Orbital period. V is the orbital velocity. Okay, or it is also known as 1 sidereal day. And it is in general 86,164.09054 seconds. Okay. Now let's find an expression for r. R will come out as cube root of, this is the r we want to find out. Okay, so r will be cube root of g me t square by 4 pi square. So we can take mu as the geocentric gravitational constant, which is g times me. Okay, g times me. So this expression will vanish because this is just constant. It is 398,600.4418 plus minus 0.0008 kilometer cube per second. Okay, second square. Okay, so r, I mean, when we replace gme by mu, r will come out as cube root of mu t square by 4 pi square. Okay. The resulting orbital radius, when you put the values of t as well as pi, it would come out to be 42,164 kilometer. Now just from this subtract the earth's radius, subtract earth's equatorial radius, which is 6378 kilometer. So we get the altitude of the satellite geosynchronous satellite as 35,786 kilometer. That is how we get to that 36,000 kilometer mark. So this is basically like this. Let us suppose this is a sphere and this is Earth. This is the center of the Earth, and this is the orbit. I mean, this is the satellite which is orbiting around the Earth. This is the radius of Earth, which is 6378 kilometers, and this the total radius because of the orbit would be 42,164 kilometer. Okay, so this remaining part is something like 35,786 kilometer. That is the formula. This is the satellite. This is the Earth. Okay. So what about the orbital speed? We know the altitude now. What about the orbital speed? Orbital speed is v, which is omega r, out of our knowledge from uniform circular motion or circular motion as such, where omega is the angular speed. Okay, so it comes out to be nearly equal to 3074.6 meter per second. Okay, with this we can move to the next part. Two major forces acting on a satellite are, okay, the answer is definitely centrifugal force and gravity. So we can take A easily. Okay, so just a common knowledge about what centripetal force and centrifugal force is. Uh, Centripetal force, I will show it using a diagram in an upcoming question also. Acting on satellite, it acts on satellite due to Earth. Okay, so when satellite revolves around the Earth, it undergoes a pulling force from the Earth due to Earth's gravitational force called centripetal force. Okay. So this, let us suppose this is F1. So F1 we know is gmm by r square, where capital M is the mass of the earth, small m is the mass of the satellite, g is the universal gravitational constant, and capital R is the distance between their center of masses. We already did it in the previous question. We also understood it very well. Okay. Whereas centrifugal force, let us suppose this is F2, when a satellite revolves around Earth, it undergoes a pulling force from the sun and the moon due to their gravitational forces. This is how we can understand it. So F2 is also equal to a very similar expression, but it is mv square by r. Okay, where v is the orbital velocity of satellite, and orbital velocity, we found it already in the previous section, would be square root of gm by r. Orbital velocity v is nothing but square root of gm by r, which is previously found itself. Okay. So one conclusion which can get out of it is that uh, g and m are constants. Okay. So orbital velocity is directly proportional to 1 by square root of r. It depends on the distance from the satellite to the center of the earth. Orbital velocity depends on the distance from the satellite to the center of the earth. Okay. Let's move to the third question. The number of Lagrange points for a two-body system is, it is a very it's a theoretical question basically. The number is 5 actually. L1, L2, L3, L4 and L5. So these are the Lagrange points. So, oh sorry, what am I doing? So Lagrangian points are points of equilibrium for small mass objects under the influence of two massive celestial bodies, massive orbiting bodies. Okay. So wherever we find that they are stabilized, so those are termed as Lagrangian points, and this actually mathematically relates to a very famous problem known as the three-body problem in astronomy, and that is why it becomes so interesting and important. Next up, the ascending pass and descending pass are satellites movement from. Okay, so they are from south to north. When the satellite moves from south to north pole, it is something known as the ascending pass, and when it moves from north to south pole, it is something known as the descending pass. So this is the answer. A is the answer. But let me just tell. But it is mostly applicable in case of polar or near polar orbiting satellites. Okay, which is the case with most remote sensing satellites. So most remote sensing satellites are in near polar orbit. Okay, means the satellite travels northwards on one side of the earth and then toward the southern pole on the second half of its orbit. So these are basically called the ascending nodes and the descending ascending and descending chord, called the ascending and descending passes respectively. Okay, so let us suppose this is the. Okay, I will explain it in another slide. So let us suppose this is a sphere which represents the surface of the earth. It is a sphere. Okay? This let this be the north pole and let this be the south pole. Earth is actually not a sphere, it's an oblong, it is a bit depressed along the poles. Okay, so the circumference of the earth, if you move along the equator, is more than when you move along the poles. So when the satellite moves like this, from south pole to north pole, it is something known as the ascending pass. Okay, and when it moves from north pole to south pole, let us say, it is something known as the descending pass. Now let's think. I mean, how are they so important? Why are they so important? If the orbit of satellite orbit is also sun synchronous, okay, the ascending pass may be on the shadowed side of the earth, may be on the shadowed side of the earth. Okay, while the descending pass on a sunlit side. Okay, so sensors recording reflected solar energy, means a passive sensor, passive remote sensing, reflected solar energy only image the surface of the descending pass. Why? Because it is sunlit. They get a greater signal in that case. Okay. On a descending pass. Okay. When solar illumination is available. So that is its implication on on the course of remote sensing. Now, what if it's an active remote sensing sensor? We talked about a passive sensor. Higher amount of illumination is available when it moves in a descending path if it's sun synchronous. So it will be able to sense the part of what which is on the descending path. Okay. What if it's an active sensor? Okay. Let's take another. Sorry. Active sensors which provide, so we know that the fundamental difference between passive and active sensors is that passive sensors detect energy from something else, from some other body, whereas active sensors they emit their own energy, which provide their own illumination, their own illumination, or passive sensors that record emitted, for example, thermal sensors, means nothing to do with the optical zone, radiation, can also image the surface on the ascending pass. Image the surface on the ascending pass. So what's the matter? The matter is that when it moves from the south pole to the north pole, it is an ascending pass. When it moves from the north pole to the south pole, it is a descending pass. Now passive sensors which work on the optical range, I mean 0.4 to 0.7 micron, if they are also sun synchronous, then more illumination will be achieved when they're moving in the descending pass. In case the ascending pass is the shadowed part, okay. So in that case, they will be able to image only that part of the Earth in which they are undergoing a descending pass. Now, what about the active remote sensing sensors or thermal passive remote sensing sensors? Because thermal doesn't require any optical measurements. Okay, so they can even measure or sense the Earth through the ascending pass, basically. So that's the basic difference. Let's move to question number 5. The centrifugal force acting on satellites is known as. So it's very simple. It is part A. It is part A. A is the correct answer. It's very simple by the way. Okay. So now let's see what actually happens. Now let us suppose this is the Earth. Okay, and or any circular motion body. This is the center. The path of inertia, if it is moving in the anti-clockwise direction, the path of inertia will take it here. Okay, path of inertia. The inward force would be the centripetal force. Centripetal force. The outward pseudo force is something known as a centrifugal force. Okay. So centripetal acceleration. So they are basically equated. So let's talk about the centripetal acceleration. Or let us denote it with AC. It would be V square by R. R is the distance between their center of masses. Or AC, I mean, according to uniform circular motion, would be also omega square R, where V is the linear velocity and omega is the angular velocity. And R is the radius of curvature. So Fc we know is mv square by R, or it is equal to mr omega square, since V is equal to omega R. Now let's move to the question number 6. If satellite moves in same direction as of Earth's rotation, it is called A. Retrograde motion, B. Prograde motion, C. Ascending path, D. Quasi-retro motion. The answer is prograde motion. Uh, so retrograde and prograde. So let's see what these actually mean. Retrograde orbit, this is the one in which satellite orbits in the direction opposite to the rotation of its central object. Central object in satellite remote sensing across Earth would be the Earth. Okay. So let us suppose this is the Earth. Earth is rotating in, let us say, the anti-clockwise direction. Okay, this is the Earth, and then at an orbital height. Okay, so at an orbital height, the satellite will also rotate around the Earth. So let us suppose this is the satellite. It is rotating in a, let us say, clockwise motion. Okay, so this is known as the retrograde motion. Now what happens in prograde motion? In prograde motion, the rotation of the Earth and the rotation of the satellite are both in the same direction. So if, I mean, anti-clockwise is anti-clockwise, that's it. So prograde spins in same direction as its orbit. So that's the story. If satellite moves with the same time period as that of Earth, then it is called A. Geosynchronous satellite, B. Sun synchronous satellite, C. Polar satellite, and D. Near polar satellite. It's the geosynchronous satellite we know very well. So geosynchronous satellite, the orbital period is same as Earth's rotation period. Okay. What about a polar satellite? Polar satellites are mostly the ones which we use for our remote sensing purposes. The polar satellite passes above or nearly above the poles, nearly above both poles of Earth on each revolution. So inclination angle in that case would be nearly 90 degree, whereas the inclination angle, the angle in case of geosynchronous satellite is almost zero. What about sun synchronous satellites? Sun synchronous. So the satellite passes over any given point on the planet's surface at the same local mean solar time. That's the basic difference. The same local mean solar time. So that's the thing about it. Next question, difference in time between Greenwich meridian and a degree longitude away is, okay, so we know that the total number of longitudes are 360 degrees, and it takes 24 hours to travel that. Take a round rotation, right? So for 1 degree it would be 24 hours by 360, or 24 into 60 minutes by 360. So this is 6, 24, that comes out to be 4 minutes. So every 1 degree increment corresponds to 4-minute change. If you have a 4-minute increase, okay. So 1 degree difference, the time changes by 4 minutes. That is what we get, and the answer is 4 minutes. The answer is B. Now let's see. What would be the time in India? Okay, time in India when it is 12 noon in London. So for that, the baseline longitude is set as 0, which passes through London in the Greenwich laboratory. So we have to just find the differences in the longitudes between the Indian Standard Time. The Indian Standard Time longitude is 82 degree 30 minutes, which passes through Prayagraj in India, and the London one is 0. Okay, so Indian Standard Time, London one or the Greenwich one, Indian Standard Time is corresponding to 82 degree 30 minutes east. Okay, so time difference would be what? Time difference would be, so for every longitude change 4 minutes get changed, get shifted. So it would be 4 minutes, and since India is eastwards, we need to add it up basically. So 4 minutes times 82.5, because 82 degrees 30 minutes is 82.5, so we get 330 minutes. Okay, which is 5.5 hours, which is 5 hour 30 minutes. Okay, so when it is 12 noon in London, we need to add plus 5.5 hours to it to get the time in India. So time in India would be, in India would be equal to 5:30 p.m. Okay, because India is eastward, so we are adding it. A geostationary satellite is orbiting the Earth at a height 6 r above the Earth's surface, where r is radius of the Earth. What will be the time period of another satellite present at a height 2.5 r from the Earth's surface? Very interesting. So let's see. For the geostationary satellite, R1 would be capital R, that is uh, that is the radius of the Earth, plus 6r. We are basically finding, this is because we need to find the distances with respect to the center of masses of these two bodies, the Earth and the satellite. So that is why we are adding 6r, adding r to it. So this comes out to be 7r. And for a geostationary satellite, we know that the time period is basically 24 hours. We don't need to be given this information, we know it already. Okay. For second satellite, let us suppose the distances in the center of masses be r2. Okay, so r2 would be again r, which is the radius of the Earth. We need to again add plus 2.5 r, which is given as given. So it comes out to be 3.5 r. Okay, so time period of satellite, we know it is t is equal to 2 pi square root of r cube by gm. Okay, where r is the radius of the orbit. So one thing which we get is that here g, m and 2 pi are constants, whether you use the expression for geostationary satellite or for the second satellite as given in the question. Okay, so if we take the ratios t2 by t1, it will basically nothing but r2 cube by r3 cube square root. So let's just put the values. T2 by 24 hours is r2 is 3.5 times r by r1 cube. So r1 is 7r cube. Okay, and it comes out to be 1 by 2 square root of 2, t2 by t1. Okay, let's finish this question. So this gives the t2 as 24 hours, t2 by t1. So that t1 in the denominator I take to the right hand side. So 24 by 2 square root of 2, which comes out to be 6 square root of 2r. Okay, we are done. Next question. Two artificial satellites A and B are at a distance RA and RB above the Earth's surface. If the radius of the Earth is r, what would be the ratio of their speeds? Okay, so let's just go back to it with the very basics. Orbital velocity of satellite let us suppose it's v, would be gm by r square root, where r is the radius of circular orbit from the center of the earth. Okay, we know that already. Now what would be the cases for satellites A and B? Let us first check for satellite A. So RA would be RA plus R. I mean, we're just adding this radius of the earth again. Okay, we're not doing anything different for satellite B. So don't forget that you always need to add up the radius of the earth with the orbital height or altitude. RB is RB plus R. Don't forget this step ever. So VB by VA is RA by RB power 1 by 2. So it comes out to be RA plus R by RB plus R power 1 by 2. So this is the slope. You're done with it. An artificial satellite is launched into a circular orbit around the Earth with velocity v relative to the reference frame moving translationally and fixed to the Earth's rotation axis. The distance from the satellite to the Earth's surface is x. Find it. The radius of the Earth and the free fall acceleration on its surface are supposed to be known. Okay, let's take it up. Let the mass of the satellite be m and the mass and radius of Earth be m and r respectively. Let's take v as the velocity of satellite relative to Earth, of satellite relative to Earth. Now we just need to equate the two prominent forces, the centripetal force with that of the gravitational pull of the Earth, and we are just going by the first principles which I showed in the first question which was discussed today. So in an Earth's orbit, centripetal force is balanced by the gravitational pull of the Earth, or Fc equal to Fg, that's the same thing. Gravitational pull of the Earth. Okay, so let's just equate. So this is on the right hand side, the term would be gmm by r plus h square. H is the orbital height. Okay, and so this is this term, and this term is mv square by r plus h. Capital R is the Earth's radius. We always need to add it up. Okay, so if you are forgetting it, that would be a huge mistake. Okay, now let's just simplify this term. We'll do it in the next slide. So we get gmm by r plus, let me write it again, gmm by r plus h square equal to mv square by r plus h. Okay, so what do we get? We get r plus h as gm m gets cancelled anyway, small m I mean, by v square. This implies h is gm by v square minus the Earth's radius. We also know that the acceleration due to gravity can be written in terms of the universal gravitational constant, which is gm by r square. Okay, so let's find h in terms of g now. So h will be g r square by v square minus r. Okay, so now let's take r as common. I mean, how much we need to find out h is x times r. So that is, I mean, so we need to find it out basically. So it is r gr by v square minus 1. So we get x equal to 1. I mean, this is what was required. A geostationary satellite orbits around the Earth in a circular orbit of radius 36,000 kilometer. Then what would be the time period of a spy satellite orbiting a few hundred kilometers above the Earth's surface? We are again going by the first principles itself. Okay, so for a satellite of mass m moving with a velocity v in a circular orbit of radius r around the Earth of mass m. We just equate the centripetal force with that of the gravitational pull. So what do we get? Okay, so from it we get v is equal to square root of g m by r. I have shown it several times today already. Okay, now velocity is nothing but the distance by time. Distance is circumferential across the Earth, so it would be 2 pi r, because it is a circular motion anyways. So v is equal to 2 pi r by t. So what do we get? 2 pi r by t, we are equating it with this term, is equal to square root of gm by r. So from it we get that t, that is on the denominator, t would be directly proportional to r to the power 3 by 2, because everything else in this equation is, I mean, g, capital G and capital M and pi and 2, these are basically constants. Okay, so capital T, that is the orbiting time, would be nothing but will be directly proportional to the to r to the power 3 by 2. Okay, so what do we get out of it? We get, let me take another slide just to finish it up. So from the previous one we get t is proportional to r to the power 3 by 2. This gives the ratio t2 by t1 is r2 by r1 to the power 3 by 2, and that's what the question is asking actually. So we know r2 equal to Earth's radius is 6400 kilometers, r1 is 36,000 kilometers, which because it is of the geostationary satellite. Okay, and t1 is also 24 hours because it takes exactly 24 hours to finish an orbit. Okay, let's just put it in equation 1. T2 we get as 24 hours times 6400 by 36,000 to the power 3 by 2. We get the answer as 1.8 hour. One last question for the day. Two satellites A and B go around the planet P in circular orbits having radii 4r and r respectively. If the speed of the satellite A is 3v, then what would be the speed of the satellite B? So we should again go with first principles again. Okay. So we know that the velocity, orbiting velocity, is square root of gm by r. So from it we get that the velocity is equal to 1 by square root of r. This is the expression. So VA by VB would be nothing but RB square root of RB by square root of RA. It's as simple as that. So let's just put the terms. For the first one, it's okay. So it's capital R by capital 4R, which comes out to be 1 by 2. Because R square root of R gets cancelled. So VA by VB is equal to 1 by 2. This implies what was VA? VA is given as 3V already. 3V by VB equal to 1 by 2. So this gives us VB as 6 times V, small v, and that's the answer. So we are done with all the questions which I wanted to discuss today. Thanks for joining. Let's meet again the next Friday.